Because that time was a little bit late and the ANI people.
Can you hear me?
Amy, I can hear you.
You
Okay.
can hear? Okay.
So are you ready to go?
Yes.
Okay, so it's a pleasure for me to announce the speaker of this afternoon is Remi Leandre, good old friend of mine, I must say. And he's going to talk about toward Wong-Zakai approximation for big order generators. Please, Remi, go ahead.
As a matter of fact, I will speak on our paper later because it's published now. And this paper entered in a beautiful probabilistic index theory of Professor Bismuth. With Bismuth proved by path integral of Brownian motion, you see the formula which are simple to check by analysis. For instance, Bismuth gives the Bering-Bering. Bismuth proof gives the Bering-Bering's proof of index theorem. And Getzler proof we are marvelous constellations you never explain, and you can see very well in my proof of the operator. It's published in Compte Rendu in 1986. So you consider L second order differential operator. Here Xi are considered as one order differential operator. And it is a second order Hoermander type operator. And you consider the semigroup, it is plus LPT here. And a semigroup with a parabolic equation starting from F. So you have classically PT f of x equal expectation fxtx, where you have a diffusion associated to this semigroup, dxt of x equal sum to y xi xt of x dwit, where dwit is a flat Brownian motion on Rm, if you consider M vector fields. It is a stratigraphic equation. So now it starts from x. You classically pt f of x equal expectation of fxtx. So classically, you introduce polygonal approximation WTN. So it is a generalized stochastic differential. It is a generalized equation, strategic equation, and you consider now a random ordinary differential equation. dxtm of x equals sigma xtn of x dwtni, where it is a random polygonal approximation of a Brownian motion. And x0 of x and x starts from x. Theorem of Wong-Zakai say to you, expectation of fxtn of x tends to expectation of mxtx. And in fact, you also whole path measure. But here you are considering only the later the semigroup, because path measure is not very well represented.
I've seen the previous version is even better. I mean, it's a little larger and we see the text. Yeah.
So now you consider xi divergence free on Rd. And you consider, you suppose you are in elliptic situation. In my theory, I've done since 7 years, it is basically elliptic theory. You consider Lk equals sum to 1 to Ck, sum to 1 to M xi2k, you are supposed elliptic theory. So these operators are elliptic. So, and they have a self-adjoint extension, they are even extensively self-adjoint, and they span a semigroup, PTK. So now you consider the analogous of flat Brownian motion we explain by a flat operator in Rm, LFK, sigma 1 equal to k, dwk dwi to k. And PTF of k of f equal, you have by elliptic theory, you have a heat kernel associated to that. Small PTF k w dw is the heat kernel associated to that. So formally, if you have formal pathwise measure, PTQ FK, and I see the formal things who leads to these things, huh? And the subgroup which is orientated as is Brownian motion by sub-integral over a formal path space FWK FW2 DQ FKW equal PT KFFW 0. If you were able to solve a formal strategic equation, dxk equals sigma xi xtkw dwit, x0 ak starting from x, all that is formal. Huh? You should have pt over x equals expression of xtkx dqfk. Is there a Wong-Zakai approximation which will explain this thing rigorously? You introduce the Wong-Zakai kernel QTKFF Wong-Zakai kernel equals to Rm F it's Rm where is M vector field Fxtwx PT FKW dw. And unlike the Brownian motion where time rescaling is square root of t, you have two k vector fields, but time rescaling in 1 over 2k. So it is, if you consider a flat kernel, this can sum to Rm Fxt 1 over 2k w P1 FK w dw. And you consider now these it is 1 x 1. You consider now this ordinary differential equation which depend from our parameter wi status x. So it is analogous to the setup of Wong-Zakai approximation for diffusion. First theorem of Wong-Zakai, let's suppose that the vector fields commute, and while you are in an elliptic situation, I suppose always you are in an elliptic situation to ensure the existence of subgroup. In my theory, with 7 years, I should have either ellipticity, either positivity. So we consider the Wong-Zakai kernel Q Fn converge in L2 of x to PTK of f. It depends here. If you put t here, it's t. If you put 1 here, it is 1. If f in L2 of x. I will give the proof later. So we consider a compact group. Xi and element of Euler algebra considered of right invariant vector fields. You consider a generalization of a Laplace Beltrami operator, this type of things. Lk equals minus k sigma I over m xi to k, and you suppose it's elliptic. By ellipticity, it has a discrete spectrum because you have a compact case and lambda associated to eigenvector f lambda. And matter of fact, lambda is larger or equal to 0 because you have 0 eigenvalues. And the theorem of Wong-Zakai said to you, to consider f lambda equal sum of f equals sum of I lambda f lambda, such that sigma LS square, lambda square, C lambda for all C strictly positive. It is a very strong hypothesis, very strong hypothesis. When the Wong-Zakai approximation converges to the gamma to in L2 to P1K of F. So if you put T here, and so on. But it works only for observed group. Wong-Zakai approximation works for a full process. I will give you a proof later, but I will give some philosophical consideration. What is the difference du Wong-Zakai approximation traditional parametrix method? You consider une principle you are on RD, and you consider this generator. You associated according to the Fourier transform in symbol. And you suppose you are in an elliptic situation. Right? It is an operator of O de P. AXXI is larger than 6IP minus C. You're in an elliptic situation. You suppose LA is positive. All is bounded, it has a self-resolved extension and generates a semi-group PTA of DF equal minus LA PTFA of P08 F equal F. And what is the parametrix method? The parametrix method, you froze the starting point, A alpha of X, and you consider the family of operator LXFY equals sigma alpha Fx d alpha dy alpha Ffy. So, and you consider a family of semigroup starting from family depends from parameter starting point, family of semigroup starting from Y. And now, what is the kernel? The kernel is f done q tp f of x. That means you consider from some depending from x, starting from x. A parametrix method, say q1 over np for n tends to p1a f x. So, and what gives this parametrix method? What is the difference of this parametric method in the case of diffusion? You know, for diffusion, Wong-Zakai approximation is very different than the Euler-Maruyama scheme of the differential equation. So, as a matter of fact, parametric method you can apply what we call the symbol to the generator upon x the Fourier transform, by this y, pt of x, pt at it is Fourier transform, and this is Fourier transform over all. And pt of x, example minus x chi f at x. And after, by using, you can invert Fourier, you can find now pt of x for Fourier transform. And it's a discrete approximation of k-order Hamiltonian perfect integral to integrate par on le momentum space. For general case. The diffusion case. So you consider your operator is equal to 2 and is equal to what? This gives you an Ito equation. And classically, it is Ito differential here. This Ito differential here, Ito equation. And classically, each subgroup is represented by the solution of the Pareto equation. And the parametrix give you the Euler-Maruyama scheme of the Pareto equation, because when you discretize the time, and you consider WIT minus WT and I. So, and when you fix X, it is a Gaussian, it is a Brownian motion, it is a Gaussian, and so the dictionary will involve this good thing. So for diffusion, I've translated a long time ago Wong-Zakai approximation in summary theory by introducing the Wong-Zakai kernel as here. It's published in a mathematical Zeitschrift in 2008. A Prof. So, you have a compact case, the operator self-adjoint to a discrete spectrum. And if you apply this to a n vector, you apply formal Fourier, formal series. And since the X-I commute, you can do commuting all these things commute. And what is the basic of these things? If you consider a flat covenant, formally, it's a group of exponential of a flat Laplacian. So, if you apply to polynomials to this, if you apply now to polynomial, if L1, Lm is not a multiplicity of 2k, it's equal to 0, because that cancels the starting point. If you apply to polynomials W1, 2k, L1, Wn, M, k, M, it is an M here, 2k, Lm, you find by applying this operator, big power with operator, flat operator, but so if you do that, after this remark, when you integrate in Wi, apply to this remark, you recognize some powers of the original and the state converge for a vector. And you remark you, and what you are on F lambda x minus 1 F lambda F lambda. You use basically commutation ratio. And so by commutativity, you find Q1 K N F exponential minus LA F PTA of F. Clean remark. And in such a case, the Wong-Zakai application corresponds to the classical Doss-Sussman representation of Stratton-Lewis is the differential equation vector fixed component. Proof of theorem 2. So you have already the same remark, but now the vector fields are not commute. So how you will do? So the first term is L F lambda, T L F lambda. And by this, because you have a term I equal to 0, because the polynomial Wi are not multiple of 2k. So, a the remaining term, you use rough estimates. If you consider ideal space associated to lambda by using the symmetry, lambda is the representation of G. And you can estimate the norms and the xi acts on E lambda. Not diagonally, we permute the eigenvector in lambda, I will act on E lambda. And so by using, you can estimate the remaining term by using this property, because E lambda is a finite dimension by electricity, and you can estimate by Gaussian inequality the boring term. Okay, so basically these tools, xi f lambda is smaller than c f lambda L square, and now you consider Gaussian inequality Lk plus C1 over 2k. It is a one order pseudo differential operator. You can apply it. It's basic elliptic flow. You want to give a reference? The paper of Doss for exasploitation. The paper of Sussman for exasploitation. And for Ikeda Watanabe, you have a beautiful book, which is a nice book. I may mention my works, and the second edition. And so now, in the Gaussian case, in my paper, mathematical statistic, in the Gaussian case, you use positivity to estimate the boring term. I've done 2 review papers on this stochastic analysis without for non-Markovian symmetric group. One is Russian Journal of Mathematics, and one is a book of pseudo-differential operator. And this paper is published in a journal of symmetry. And for implicity, basic things of implicity, because basic things of implicity are basic tools of index theory. We have a nice book of detailed book of index theory. All these things are very well explained. So now I speak a second paper, the flow theory for big order generators. So it is published to be published in a book in honor of Professor Polovich. And in fact, I correct a mistake I've done in a paper 8 years ago. So you consider still you work on RD. You consider vector fields on without diversity. All is bounded. Suppose all is elliptic, bounded elliptic. All is bounded. So you can assume by existence of subgroup on L2dx by electricity theory. It works on continuous function on RD. So now we consider the space of anti-variable matrix on RD. RD cross GLD, and you consider the vector fields on this space x dot x and dxg. dxg. And you consider now x dot is you consider the R measure on GLD, and x dot is lower divergence on a bigger space. And you consider now this big operator on the unlarge space, which is positive symmetric on L2 dx cross dg, and therefore it is absolutely defined. It admits a self-adjoint extension which generates a semigroup. Now, if you consider hx of one forms on RD, you consider h dot xg a function on the total space, which values in forms h dot xg equal hxg. And the further Blagojevsky differential minimize, if you take here you take only derivative in x, dp tot f tot equal pt tot df tot. Now, where is the problem in this theorem? This now the bounded. So you have I will overcome a problem. Blagojevsky differential is differential of stochastic differential of dependent parameter, and Malama it is the flow, diffeomorphism. So we can use in GLE. I'll give you a heuristic. You consider, as before, a flat operator, which is valued on Rm. You consider y measure element of Rn, and Pt of you consider a flat operator as before, which we generate a semigroup of CBF. You have a formal part measure dqfw. And formally, the flat kernel, the flat semigroup is represented by a formal expansion, formal flat measure. You have a formal stochastic differential equation. And formally, you have still representation of curve semigroup in terms of formal stochastic differential equation. And how you do as for diffusion formally. It is explained how I'll find this formula. You'll find this formula in my paper. Because this formula are more or less miraculous. So, the proof of very simple. You consider y1, yl a collection of vector fields on Rm. You consider all Rd. You consider y1t dot yl dot. And you gave the basic formula. Here, you take only derivative x, and here you take derivative in x and g. So, if you take dyf dot xg, take dyf of xg, you apply the differential parameter, you find number 2 fx and yg, plus number 2 f de y divided dxg, and you find this formula y dot df dot xg, because number 2 f is symmetric. And you need a question. You consider algebraic proof, d over pt of dt of f equal L of pt of f. So d over dt dpt dot f, you take only derivative x, which okay, equal dl pt dot f ptf dot equal L dot dptf. And dptf dot and ptf dot df dot satisfy the same parabolication with same initial data. So now the problem is the estimate. Now, to solve the problem of estimates, you use Volterra expansion. You consider the big semigroup is equals the big generator is equal L, the original generator, plus a differential operator of degree 2k globally, linear in G, and degree smaller than 2k in X. For a flat kernel, you use the basic fact Pt of X is equal to L2 PT xy fy, not for original kernel, PT fy dy, where RD is a differential operator of the smaller of 2k reduced with estimates. C'est pas equal facts. And now you apply Volter expansion to PT dot df dot. You have PT df dot plus a sum of iterated integrals, and R is linear in G. So you apply R to G, you find still a linear expression. It's a basic remark. And so a series converge. And now I conclude by the proof of basic facts. So, Molchanov, we use available measure theories to study short-time behavior of diffusion process rescaling, and Greiner used this in terms of operator theory. So, and for big, Molchanov works only for two diffusion process, and Greiner works for other differential operators. So you do this rescaling, and you find T1 over 2k xy are in xt of x. TL is transformed to LT, which is elliptic, still elliptic. When you scaling, but this is degenerating, and these are not degenerating, but this is tending to 0. T. So LT span a Smith group P or LT elliptic, the non-generating of semigroup span a semigroup, and you have a basic remark. PT equal P1T. And so you have this formula. And you use P1, PT01 equal T minus 2 over 2K, P1T01 2 over 2K. So it remains to show we estimate some non-degenerating elliptic group. Number of x P1T of 0y is smaller than C exponential minus y. For that, use the David-Gauge transform. You multiply the test function by exponential cy. And you do this, and by elementary computation, is equal to LT to the participating term of law. Now, Davis does that for a level of equal forms, and here you do that for a semigroup. And you deduce, and you have an estimate for gauge transform semigroup. The semigroup is still gauge transform, and P1T here, P1T, P1 over 0.1 is minus CI. And you do the electric form. So, I correctly estimate, I'm going to estimate 8 years ago. So, go reference. You have marvelous books of Hiroshi Konita. And my paper will appear in Peshri for Nobrovich. And in one dimension, for four operator, I have a paper Geometric Information Conference World Paris. And for these things, with elementary construction of guess also a paper of Davis. Good. So I've got some paper, some document we show to you following my test. Some people don't like discrete mathematics, but I'm wrong. If you want, I can show. If you don't want, some people don't like discrete mathematics, but I'm wrong. So I thank you for your interest.
Okay, thank you very much for your talk, Remi. So, are there any questions or comments?
So my theory it remains to understand, I've understood involvable elliptic. Basically elliptic fields. It remains to understand very well stochastic differential equation. Calculus, I understood.
I have, Remi, I have some question. Can you go back to the beginning of your talk when you first time write down the operator LK? So that means sum of vector fields at the very, very beginning. Maybe it was page 3 or so. Yeah, it's here already, I think, but okay. Because there's something I did not understand or maybe misunderstand. And this is already the symbol form, just the original one. A little bit down, maybe. Where's this operator? So this is sum of squares. I think it's on the next page. Yeah, yes, yeah. So this K, this is any natural number.
A natural number, yes.
Right. But now if you look at this operator, yeah, if you look at this operator and you look at the heat equation, so the corresponding semigroup PTK, it will in general not be positivity preserving, right?
No, it changes the sign. Problem changes the sign completely. It's not Markovian.
Okay, so it cannot represent, it cannot be represented by any kind of process because the transition semigroup for a process is always positivity preserving, right?
Yes, yes, but I given the formal consideration.
Okay.
Actually, to this formula, in order to show how I found the formula.
So when you talk about kernels, these are not probability kernels; they're not non-negative.
No, the chain of sign.
Okay, okay. So that is what I didn't catch.
Between Markovian semigroup and non-Markovian semigroup, because you've got plenty of semigroup by elliptic theory, but generally the semigroup are not Markovian.
Right, and these representation, nevertheless, you get by some probabilistic considerations, right? Because otherwise, it's not clear whether such a kernel exists, even if it is not negative, not non-negative.
The kernel exists by ellipticity, by elliptic absorption.
Okay.
Because if you consider a positive adjoint symmetric operator, the semigroup has a lead kernel.
Okay. So
but the kernel is not positive, it's chain of signs.
Okay, now I understand. You just use some kind of hyperellipticity, you find the kernel.
It would be very understood to state by these things Hoermander's theorem, because there is no Hoermander's theorem for big-order generators.
I see. Okay. Okay, Enrico.
Yes. So my question was actually related. So when you say non-Markovian, it means not that you have an underlying stochastic process that is non-Markovian, but it just means that the operator you are starting from is not connected to a stochastic process because it's not essentially positive or.
You have a stochastic process that generates by Hahn theory. You have a stochastic process where the generator satisfies the maximum principle. If the operator does not satisfy maximum. And the chain of sign, everything of the don't present positivity. So, and analysis value against the probabilistic method, because they say you have much more operator, but operator represented by stochastic process, and method works. So, for one in my theory, because I've done several papers in this direction, no real new results with respect to analysis, but fulfill a gap. I've done Malama calculus or big order generator, type of things. And now, Malama calculus, it's related to the topic of this conference directly, because I perturb positive pseudo-differential operator on compact manifold by a fractional power of it in Seeley theory. I can establish Malama by part in 20 lines. And so Malama by part would deduce a semi-group as a density. And so now I think analysis I think Professor Malama should be very satisfied by this theory, because it fulfills a big gap in analysis. But of course, now for a man, nothing really new with respect of tools of analysis, and but fulfill a gap. I've done several conferences in analysis, so I've done large variation estimate for a semi-group or two, but for absolute value, always absolute value, because the generator change signs.
But this PTK is still Hilbert-Schmidt operator, and that's the reason why you get the kernel. Is this correct?
You get a kernel. You get
because
a kernel.
PTK, you're on a compact. You're on a compact manifold or not?
Compact manifold, yes. Compact
right,
manifold.
Then this is
but
yeah,
you have kernel
okay.
too in non-compact manifold with a uniform ellipticity assumption. Ellipticity.
Yeah. Because otherwise you don't have the kernel.
No.
You need Hilbert-Schmidt, I guess. Yes.
Uniform ellipticity, all bounded or non-compact manifold to have a kernel,
Yes, but not in the case where you don't have positivity preserving. I don't know this theorem. Maybe you know another theorem. I just don't know.
No, it's Davis. He had got the rough estimate for each kernel on RD. Satisfying some type of hypothesis by using Dirichlet form, that of things. And so,
but there is no Dirichlet form here because it's not second order or lower order. There's no Dirichlet form. I don't know, at least. Because you don't have the contraction property for these operators. It's not a Dirichlet operator for sure. So I think one needs some kind of, maybe in Davis' book he has some case. I don't remember.
This what you can show there is a lead kernel by inverting Fourier transform.
Okay, yeah, this is probably possible. Yeah, I agree.
You can, because here you have explicit formula by Fourier transform. You can invert the Fourier transform and show it converge.
Okay, are there any other questions or comments?
So may I ask another question? So let us stay on this page, and I wanted to ask you if you know any physical system that could be described by this semi-group.
I don't know. My goal was to fulfill a gap from I don't know. My goal was to fulfill a gap with analytical things. Because analysis, they were very ugly with Malama calculus, because it was working only for semi-group represented by stochastic differential equation. I don't know. But you have a huge literature, big order differential operator, and so a huge differential, and a huge literature, but
okay. Any other questions? Yeah, then let us thank Remi again. Okay, and probably you know the talk at the, I think it was